All right. So this is the problem we're going to work today, or one of the problems we work today. And we want to construct the shear force and bending moment diagram for this problem. It's a cantilever structure, as you can see. It has this very odd loading combination on it. Some negative uniformly distributed load here near A, and then some uplift force kind of down here at the end. So the first thing we want to do is draw a free body diagram of the whole structure. And at my support condition, I will assume a positive shear and positive bending moment for my reactions. And then I'm going to take these two loads and make a concentrated force equivalent of that. So looking at the first one, we want to make sure that the area under this distributed load is the same as our force. So the area is a rectangle, so the area would be 8 times 800, which is, what is that, 6,400? I'll just go ahead and do it in kips, if that's okay. So I'll end up with a load of 6.4 kips. It's going to act in the centroid. Since it's 8 feet long, the centroid will be 4 feet from either end. So I'll go ahead and put 4 feet there. And then down here on the end, I have another one, identical area, but it is up. Same value, 6.4 kips. Also, in the centroid would be 4 feet from each end, so I'll put my 4 feet there. And of course, the middle section then would be 4 plus 4, or 8 feet. So there's all the pieces that I have. Did I get that right? You guys like that? So now I'm going to sum moments with right-hand rule as my sign convention, and I'm going to do it at A. That's a good place for this problem because the shear at A won't create any moment there. So I'll get one equation and one unknown, in this case the moment at A. So now that I'm using right-hand rule for my sign convention, what kind of moment is this? It's negative. And about A, the first 6.41, the one that's going down, what kind of moment does that create? Positive or negative? Negative. So the force will be 6.4 kips, and the distance 4 feet. Now about A, this concentrated equivalent out here that models this distributed load is going to create positive or negative moment. About A. Positive. The force is 6.4 kips, and the moment arm for that is 12 feet. So what is the moment at A equal to? It looks like it's positive, and I don't know what that is. What's 6.4 times 8?
51.2.
Say again?
51.2.
51.2. Did you guys get that? 51.2? And that will be kip feet. So it looks like the moment at A is positive. I'm sorry, the bending moment at A is positive. And now we can come back and sum forces in the y direction. Make sure that's in equilibrium. I'll assume up is positive. So looking at my free body diagram, my shear is up. That's positive. This 6.4 is down, so that's negative. And this 6.4 is up. That's positive. So it looks like the shear at A is, interestingly enough, 0. So I know my starting points. By the way, when I get all the way out here at B, what's the moment at B? At the free end?
0.
0. And what would be the shear there? Also 0. So if I construct a template where I'll have my beginning and end of my beam, something's going to happen here right at 8 feet because I'm going to have a transition from a negative load to a positive load. So I think I'll add that to my template 2. So to get started with my shear diagram, I am going to establish a positive x-axis, a positive shear axis. I'm going to assume all my shear values are in kips. And let's see what I've got. I've got, well, I saw for the shear day, right? So the shear day is 0, so I know I'm going to start here at 0. We go all the way to the other end. You'll notice there's no applied force at B, so probably the shear there is also going to be 0. Not probably. The shear there is 0. So I've got to figure out how to connect those 2 points. Now remember, our integral relationships tell us that the change in shear between any 2 points is the area under the load diagram. So the change in shear between or over the first 8 feet should be equivalent to the area under the load diagram, which is what? We found that already, 6.4, and it's negative. So 0 minus 6.4 is negative 6.4. And the shape of this curve should be given by the value of the load. And if we look up here, the value of load is constant. So constant slope is a straight line. And it's negative. That's a negative slope. So we get that for our shear diagram over the first 8 feet. Now from 8 to 16, or this next 8-foot segment, the change in shear should be the area of that part of the load curve. So I go up here and look at that, and that's positive load, right? Up is positive. So I get the same 6.4 kip load, but it's positive. So obviously negative 6.4 plus a change of positive 6.4 brings me to 0. Excellent. And the slope is equal to the load, and the load is constant. So a straight line and positive. So here's a slope. Here's a line with constant positive slope. So now your shear diagram is this triangular shape here. Any questions about that? All right, so I feel pretty good about the shear diagram. Let's move on to the moment diagram. So I'm going to start by establishing a positive x-axis, positive moment, and I'll say all my units here will be in kip and feet. Now what do I know about the moment? Well, I know the moment at A, I solved for it, it's 51.2. So I'm going to start at a positive 51.2. And I also know the moment at the free end. What is the value here? 0. So I should come back to 0. Now I've got to figure out what happens in between. And to help us do that, we can use our integral relationship for moment, that the change in moment is the area under the shear diagram. So let's see if we can do that. So starting at 51.2, I'm going to change based upon the area of the shear diagram over the first 8 feet. I'll double hatch that one so you can kind of see that's the area we're working on right now. So what's the area of that part of the curve? 51.2. Is it? Yeah. So it's the
2.2.
That should be half that.
Yeah, half that.
It should be 8 times 6.4 divided by 2. So what did you get? 25.6. And if you subtract that from 52, you should get, what was the number again? 25.6. That's right, 25.6. And what's the shape of the curve here in between? Well, that's given by the shear. We know that the slope of the moment diagram is equal to the shear. So what is the value of the shear as we start here at the beginning? It's 0. And it increases to a large negative value. So I'm going to start off with a 0 slope, and I should get here some kind of negative value. So I'm going to get kind of a little parabolic section here. Now the change from 25.60, that should be governed by the area of this part of the curve, which again is another 25.6 negative, right? So 25.6 minus 25.60, great. Now, the shape of the moment diagram is given by the shear. The shear here is still negative 6.4, so that's good. And it decreases to 0, so I should have a 0 slope there. And if I fit something through that, it should look something like that. So you get a parabolic curve over the first 8 feet, and then it kind of flips over and you get a different shape. Still parabolic, but a different shape. And that is your moment diagram. So if I were to ask you a question, what's the bending moment in the middle of the beam? The answer would be 25.6 kip feet. Any questions about that one? All right, excellent. That took us 10 minutes to do.